Welcome to this introduction on quantum computing. My name is Daniel Hook. I'm a trained physicist, hold an MBA, and I worked for many years for Credit Suisse and UBS in transformation in wealth management. Meanwhile, I'm in quantum computing, helping companies to understand capabilities, chances, and risks of quantum computers and how to prepare for and make use of them. So let's go in here. Let's start with the basics. What is a quantum computer? There are two types of quantum computers: gate-based digital quantum computers able to execute arbitrary quantum circuits. So this is the actual quantum code. And there are analog quantum computers like quantum annealers. Maybe you heard of D-Wave. Annealers can solve optimization problems by a physical process of cooling qubits, but they cannot execute quantum code in a narrow sense. We will focus here on gate-based computers and not on analog annealers in this presentation. So again, what is a gate-based quantum computer? A quantum computer is a device that initializes qubits, applies quantum gates to execute quantum circuits, and measures qubits to produce classical outputs. Simple as that. So the actual building blocks of quantum computers are qubits. Qubits are little two-level quantum systems that follow the laws of quantum mechanics. Their behavior is based on four fundamental quantum phenomena. There is first of all, there is superposition. A qubit can exist in a blended state of 0 and 1. Quantum gates transform these states within the qubit. And you see here these brackets around 0 and 1. This is just for your information, a quantum mechanics notation, the Dirac notation. For our purposes here, we just can use it as it's the state of 0 and it's the state of 1. Then let's go on. The next phenomenon is quantum interference. Qubit states have a phase. That phase can enhance or suppress measurement outcomes, and this is the actual superpower of quantum computers. So all the algorithms we're looking at are based on quantum interference. Then we see that there is entanglement. Qubits can be connected to other qubits in a way that you cannot describe the new joint state by single qubit states. You must treat it as a two qubit state. It's more than just a correlation, I would say. And the last one is measurement. A measurement of a qubit always returns a binary value, 0 or 1, based on the probabilities of the superposition of a qubit. This is quantum physics beyond classical. Best is not to try to explain these aspects with any mental models, but just to try to understand how they act. Forget about the how is that possible questions. How can Schrödinger's cat be alive and dead at the same time? These are more philosophical questions, also interesting, but they will not help us to understand quantum computing. There's no classical analogon. It's really quantum physics we are looking here at. We saw that qubits show a specific quantum behavior. How do quantum computers make use of these qubit features and calculate and get a meaningful result? Quantum computers are really different from classical computers, and we're still learning how to best use them. What we can say is that maybe classical computers process computation step by step, and quantum computers, they evolve a quantum state and use interference to reshape the probability distribution, the outcomes towards a desired result, obviously. Operational pillars in quantum algorithms. So what's basically what's the key content of quantum computers, the key drivers. It's phase and interference to select and mark candidate solutions. Then entanglement for correlations, obviously. Repeated measurements to gather probability information. We'll have a look at that in a minute. In an example, shaping the probability information towards low-cost solutions, and low-cost here obviously also in terms of a cost function. So we are looking for optimized solutions. All these matters when decision spaces become large, too large for explicit brute force searches, and one needs to rely on heuristics, then we can use quantum computing as an additional tool for this. Much more efficient in theory, and yeah, let's find out how far we can get. Let's compare classical bits and qubits for a start. So if you look at the possible states, a classical bit can be 0 or 1, never both at the same time, just 0 or 1. A qubit can be 0 or 1 or a blend of it. So it can be half 0, half 1, something like that, in a so-called superposition. And this is about probabilities. So the qubit can be, if you measure the qubit afterwards, you will get an outcome which is based on these probabilities. So if we are in a balanced superposition, like there's the same probability to measure at 0 and 1, each of those two states, 0 and 1, have the same probability. That's one of the key differences, but not the only one. And looking at phases, a qubit state has a phase. It's not unlike the classical bit. There are no phases in classical bits, just 0 and 1, nothing else. But a qubit can have a phase, or no, does have a phase. In a simplified view, you could say that a phase is, you can see as like an extended sign. For instance, if there is a 0 state, there is also a -0 state. Yeah. So adding amplitudes 0 and -0 means opposite phases. So there's a minus is just the opposite of the plus. Then they will cancel out if you add them together. And this is called quantum interference. A phase is much more than just plus and minus. It's like a 360-degree direction of the qubit state. So in a qubit state is like a vector aiming in additionally into any direction, 360 degrees or 2 pi as a direction. Then let's look at the state space. A classical bit always is in the state space of 0 or 1. In the qubit, you have to differentiate. There is a state space before measurement, and there the qubit lives in a two-dimensional continuous state space. We already discussed a probability distribution between 0 and 1. So there is, and that's an inner kind of degree of freedom of a qubit before measurement. And that can be between 0 and 100% for one state, and the other state is just 1 minus this probability, as you only have two states, and the measurement must be 0 or 1. It cannot be anything else. And as a second dimension, there is this phase delta between 0 and 1. It's only the actual freedom, or the actual dimension is only a delta. It's not a global phase, like both states do have a known phase, but at the end, physically measurable is only the delta between the two ones. And therefore, the qubit lives in this two-dimensional continuous state space. Probabilities between 0 and 100%, or 0 and 1, whatever you prefer. And in the other dimension, the phase delta between 0 to 2 pi. This is before the measurement. During the measurement, you always get a binary result as well, similar to the classical bit, or the same. You just get 0 or 1, nothing else. No superposition. You cannot measure a superposition directly in one measurement. And this result is based on the probabilities of the qubit states. So if you have, as our example was, 50% probability for state 0 and 50% for 1, that means you measure with a 50% chance randomly 0 and also 1 in this case. And another interesting thing is, after you measured a qubit, the qubit collapses into the state you just measured. So you cannot remeasure it. You will always get the same. And you can remeasure it, but you will always get the same result afterwards. So it's, maybe you see it's a little bit different from classical bits, what we have here. Let's examine this dual life of the qubit before and after measurement in more depth. First, we need to understand the concept of a quantum circuit. This here on the screen is a quantum circuit. It looks like an electrical circuit. You can see here the 5 qubits, Q0 to Q4. And you can see the qubit wires going from left to right. And you also see the quantum gates here, these boxes, and also these connectors here. These are all gates which are applied to the qubits in a sequence. Yeah. This is another example of a quantum circuit, so actual quantum code. Yeah, it's a simpler version, just with one qubit. But everything else is kind of similar. You have one qubit. Qubits are always initialized in state 0. Then you apply a first gate, which is called a Hadamard gate. It's not important. The details of these gates we don't need to understand in depth. It's just maybe for your information. It's an Hadamard gate does move a qubit which is in 0 state into a balanced superposition, which is 50% 1, 50% 0. And then you have further gates, like they turn these vectors around. Then the X gate, for instance, is a NOT gate. It swaps the probabilities for 0 and 1. Yeah. And if you take now this mini circuit and examine what's happening in a qubit when executing this step by step. So we'll do that. We see here again this circuit. It's the same as before. We are now in the position start, then H, then we get the various qubit quantum gates, and we end in the position end. In the start position, you see below, we have the qubit inner life, if you want. It's a 100% probability to be in state, to measure state 0. That's the initialized state, and 0% probability to measure 1. And the relative phase is undefined because you only have one position. It's not a superposition. It's a basis state, let's say. If we can now go through this step by step, and we see what happens within the qubit. Let's do that. Now we are at the H gate, balanced superposition. Then we turn X gate swaps the probabilities, and then this is the end state. So in the end state, after executing this simple circuit, the qubit has a 30% probability, if we measure it, to deliver 0 as a measurement result, and 70% to deliver 1. And we have also a relative phase in there. And now the question is, what will we measure? We do one measurement. A single measurement delivers a binary value. And this binary value is 0 or 1. Yeah, just 0 or 1. No probabilities, no nothing, just 0 or 1. With a 30% probability, you will measure 0, and with a 70% probability, you will measure 1. But it's random. You don't know actually what's coming out in this case, because it's not 100%. And okay, what that doesn't help a lot to understand the inner setup of the qubit. But what you can do, obviously, is you can repeat this several times. You need to repeat the circuit execution again, and also the subsequent measurement. So you need to do both, because if you just measure again, as said, you will just measure again the same result you had before. But if we measure this now, let's say 1,000 times, we do 1,000 shots on this circuit, as it is called, then you see in the result, okay, you get more or less 30% state 0 measurements and 70% state 1 measurements. So you found a way to get the information out of the qubit here. So through multiple measurements and executions and measurements, you get this information, but only on the probability, not on the phase information. Okay, so much to the life of a qubit. I hope it became a little bit more transparent. And then the next question might be, okay, what technology is used to build such a qubit? I would say there are three various possibilities. Let's look at the top three ones. We have superconducting qubits. These are electrical circuits on a chip where quantum states are stored in microwave resonators. They deliver fast gates, but require very low temperatures. So you need to cool them down, which is expensive, which is takes time and so on. Then there is trapped ion qubits. These are individual ions held in electromagnetic traps, where qubits are encoded in internal atomic states and controlled with lasers, offering very high fidelity and flexible connectivity. So this is very interesting. It's much less. It shows much fewer errors. It's more stable than superconducting qubits, but on the other hand, it's also super slow compared to the versions of IBM and Google. So it takes about 1,000 times longer to execute a circuit than with the first technology. But you can do deeper circuits on trapped ion systems. Yeah, it's there are advantages and disadvantages, for all the technologies. Then there's the third one worth mentioning. This is neutral atom qubits. These are arrays of laser-trapped atoms, neutral atoms, where qubits are atomic states and gates are mediated by controllable atom-atom interactions, enabling large reconfigurable lattices. This is important because you need the connectivity is also a critical point. If you can also entangle, for instance, entangle qubits which are nearby often, and therefore if you can configure the lattices of the qubits in a flexible way, that helps a lot, yeah, to reduce the overhead of computations. Yeah, at the end we can say it's different physics, but it's always the same model. It's qubits, gates, measurement, circuits. It's always the same thing. You can execute the same code on a IBM as well as on a continuum quantum compute. Okay, that's so much on what is a quantum computer. I hope you got some information out of it. You understand a little bit more or better what this was. Now let's have a quick intermezzo with our Hello Quantum World episode. Let's start with a fun fact. In classical physics and everyday processes, there is no true randomness. Even something like rolling dice is in principle fully deterministic. It only appears random because the outcome depends extremely sensitively on initial conditions such as position, angle, force, and air resistance, which are practically impossible to measure and compute exactly. Quantum mechanics is different. Here, randomness is fundamental, not just a lack of knowledge. With quantum computers, you can generate random numbers very easily. You just prepare a qubit in a balanced superposition and measure it. You will get a random result of 0 or 1 if you do not use a simulator, obviously. So if you use this for our first quantum circuit, we can generate a better than life 8-sided die. Yeah? With the approach I just mentioned, we put a qubit or 3 qubits, if you want to have an 8-sided die, 3 qubits into a superposition, and then we measure the 3 qubits and we'll get a random number, which is our result. In order to do that, we first need to define the quantum circuit to be implemented. I just described it. Here you see the diagram. You see the 3 qubits, Q0 to Q3, and you see the 3 classical bits you have as the container for the measurements. Then you put everyone into a balanced superposition. So 50% probability for measuring 0 and 1, and then you measure super simple. Yeah? So this is our circuit, and if we can use now IBM's Qiskit package, which is based on Python. We get this kind of super simple code. We first import the required classes. Then we define the quantum and classical registers, 3 qubits and 3 classical bits. Next, we build the circuit gate by gate, apply an H gate to each qubit and then measure each qubit into its corresponding classical bit. We can print the circuit as a sanity check, and afterwards we need to define a backend. In our case here we use a state vector sampler, which is a simulator, and then we run the job on the simulator. In this case, we can also do it on real hardware. Could do it and get the result back. We just need one shot. You remember, shots is the number of executions you do in order to see the probabilities behind, but it wouldn't help a lot if you have a balanced superposition and you do 100 shots, then you will probably see 50-50 distribution. We just need one shot because we need a random number. And in our case here in the code, you see the measured bit string is 001, and the random number is therefore 2. You have to add 1 because the die starts with number 1, not 0. And there we are. So this is the first quantum computer, quantum code you executed or you prepared. We can do the same. This was using IBM Qiskit package. We can do the same using Google Circ package. Same circuit. The code is shown here. The syntax and the object model look different, but conceptually it's identical. Define qubits, classical readout, apply the Hadamard gates, measure, then execute on a simulator or hardware backend. So it's, yeah, absolutely the same. You get a different result, which might be normal, but that's it. So as we saw, we had an example using the Qiskit package of IBM and also the Circ package from Google. Another important framework is PennyLane, which is widely used for simulation and quantum machine learning. There are other frameworks as well, often driven by vendor platforms. But the key point here is that these tools differ in how to encode and run a circuit, but not in the circuit or the algorithm itself. So it's just how to map it on this in this framework. Now let's have a look at a real finance algorithm, QAOA. But before we look at this, let's briefly set the context of today's quantum computing environment. Current quantum computers, including most quantum as a service offerings, are limited to roughly 100 to 200 physical qubits. These physical qubits are fragile. Their quantum states typically remain usable only for milliseconds at best, which we call the coherence time. On top of that, every gate operation introduces additional error. As a result, gate fidelity directly limits how deep and complex a circuit can be. Because of this combination of noise and limited coherence, today's devices are referred to as NISQ systems, noisy intermediate scale quantum computers. In the future, we expect fault-tolerant quantum computers where logical qubits and active error correction remove these limitations. But that is not where we are today. For current NISQ devices, we must keep circuits shallow and noise tolerant. This is exactly why hybrid quantum classical algorithms are so important. They respect these constraints and are usable on today's hardware. That's why in this session we focus on hybrid algorithms. QAOA, Quantum Approximate Optimization Algorithm. A hybrid variational, that means a tunable, optimizable algorithm for combinatorial optimization. QAOA can be viewed as a circuit-based digital counterpart of quantum annealing. You also start with a QBO, and then you find low-cost solutions. And QAOA is NISQ ready. So let's define the problem to be optimized. The objective is to propose an efficient portfolio of securities within defined constraints. We have an investment universe of 10 pre-selected shares. Each share can be bought at most once or not bought, so it's just 0 or 1, and the budget is $800. Based on that, we have 1,024 possible portfolios. Our metric is to maximize the portfolio Sharpe ratio. And let's have a look. These are the the shares I selected. It's 10 shares from Standard & Poor's 500, and we have here the returns and volatilities for the period of June 24 to June 25, and the correlation matrix of those. Here we see each of the 1024 portfolios in the risk return plot. Each dot is one portfolio here, one possible combination. If we add the optimization metric, the Sharpe ratio, then we see here the colors. The more yellow it is, the better. The higher is the Sharpe ratio. And you see here also the discrete efficient frontier. And our objective is to find portfolios on or near the Markowitz efficient frontier. Okay, let's understand the step-by-step approach for QAOA. First, we have to rewrite the cost function as a QAOA function, quadratic unconstrained binary optimization function. We initialize the qubits in a uniform superposition over all bit strings, meaning we start by considering all candidate solutions in parallel. Next, we apply the cost layer. This layer encodes the cost function by applying phase shifts to each basis state, proportional to its objective value. After that, we apply the mixer layer. The mixer redistributes probability mass between candidate solutions. Together with the cost layer, it allows interference to increase the probability of sampling good solutions. Then we repeat these two steps several times to increase the probability of observing lower cost solutions. In nowadays computers, quantum computers, you cannot do too many repetitions due to the depth of the circuit. If you have too many, the depth will be too high, and then noise will destroy your results. Finally, we run a classical optimization loop that tunes the QAOA parameters to minimize the expected cost. Once the parameters are optimized, we execute the circuit with many shots and read out the best bit strings from the measurement outcomes. So this is how QAOA works in a nutshell. Yeah. What you see here, this blue is the preparation part, and here the darker amber part is the quantum computing execution part, and then you have a classical optimization and the final just readout of the, or you need to execute it as well, but then afterwards you have to read out the final result. This is a generalized view of the standard QAOA circuit. UC and UM, the cost and mixer gates, are shown as a block. So here you see for each layer, you see each one UC and UM. It looks simple, but in reality they are complex circuits, each one with many sublayers and qubit gates. So this is quite a complex circuit. The number of the layers is a hyperparameter to be optimized for the task and underlying hardware and noise level, as mentioned before. First step in a QAOA is to define the QAOA. The cost function expressed as a function of the bit string x. So this QAOA here, this function shall be minimized. That's our cost function. In our example, it contains a linear return term, a quadratic risk term, and a budget term here. This last part here. The weights of the QAOA must be thoroughly tuned. Here we see the three QAOA terms plus the total of all 1,024 portfolios plotted over the total spend value, one of our objectives, remember? And we see that the linear term is linear also in the total spend. And the other one, like the green one here, is sharp because we are looking at it on the spend axis. And therefore, we can see that it's a perfect curve at the minimum at the target budget of $800. But you have to tune it to make sure that the weights are correct. So what's more important for you? Is it the risk? Is it the return? Is it the budget constraint? And this will then lead to the final result with a respective bias. When you tune it, you will see that there is, for instance, if you look at alpha for the budget, if alpha is 0, this is a straight line, the green one here. Or if we have it at 1 or 2, this will narrow the other distributions if you put more emphasis on, for instance, budget, and so on. Here we see the results of our experiment. On the left side, all possible portfolios colored according to their Sharpe ratio. Gray dots here are out of budget, out of the boundaries for our budget. And on the right side, these are the portfolios which have been selected by the algorithm. You see, it's not only good selections, but we have 2 of the 3 top portfolios we have in our selection in this run. This here is another view. Here we see the selected portfolios in blue here. These are the selected ones, and the gray ones are the brute force available portfolios. The blue ones are also, there are also multiple counts in there. That's why they exceed the gray ones partly here. As you see, the result looks loosely grouped towards the target here, the budget, but it is not a hard selection. You can do that also for the other dimension of the QAOA, but in general, you'll find similar results. And if you take the time, you can improve the situation, and there are some additional tricks just to make sure you get better within the boundaries of your constraints. So this was QAOA. Now let's have a look at QML, at the next NISQ-ready algorithm, quantum machine learning. We look now at VQC, Variational Quantum Classifier, an example for a quantum machine learning algorithm. And it is also NISQ ready, as mentioned before. In a classical neural network, you optimize the weights between the neurons to perform learning. This happens through backpropagation. In a VQC, you first encode the features and then apply a variational ansatz block, which is a specific circuit, a template circuit, and then you can optimize the parameters of this ansatz block classically in learning cycles. At the end, you measure the results. That's in a super nutshell the principle. And now let's walk through the VQC step by step as for the QAOA. First, we define the learning task and prepare the data set, including train and test split. Then using angle encoding, there are also other ways to encode features, but we use angle encoding. It's the best way to do when having NISQ computers. We encode the features as phases in the quantum state. Then we apply a trainable quantum circuit. and measure to produce a model output, for example, a class score. We then run a classical training loop, evaluate the loss on the training data, update the circuit parameters with a classical optimizer, and iterate until the loss stabilizes, similar as you train a classical machine learning model. Finally, once trained, we run the same circuit on the test data and evaluate performance with standard metrics. Using this angle encoding method, as I mentioned, you load one feature value to one qubit, which is quite efficient. With 10 qubits, you could load 10 full features into such a circuit. This is the VQC quantum circuit, feature encoding and the trainable ansatz block, which will be trained in the training loop, as mentioned before. And this will be done classically. And this is why the whole thing is NISQ ready. The actual quantum computing part is very short. You just execute this once, and then you measure out all the results, and then you optimize classically. So this is, you do it a lot of times, but every time is a short exposure on the quantum computer. That makes it feasible for NISQ devices. If we compare the QML approach with classical machine learning, we can see we need to pre-process, normalize the data, the phase to the phase range of the qubit. So typically from 0 to pi or 0 to 2 pi. Then we need to split the data in training and the test data at least. The feature encoding is done through a sub-circuit feature map. Then the variational ansatz, which will process the data, relates to the neuron layers in a classical setup, in a neural network. The output layer is simply the qubit measurement. You don't have any softmax layers or something like that. And the training loop is done through a classical optimizer. We also need to tune the hyperparameters like tune feature map and ansatz, learning rate optimizer, and stuff like that in order to get better results similar to a neural network in classical machine learning. Let's apply this approach to a real data set. We use a popular Kaggle data set on credit card fraud detection. You find it on the internet. And the data set is highly imbalanced. It's about 285,000 transactions, but only 492 are fraud cases. And therefore, we reduce our data set to a subset of only 984 transactions. So we get a one-to-one fraud and legitimate transactions balance. We use 80% for training and 20% for test cases. And we only focus on the 5 top features. These are in total 28 principal component analysis features. So these are the result already. This is the result already of some optimization. And these 28 PCA features, we only use the top 5 of them with the most impact on the result. And here we get the result. After all the reductions on the data, the result is we got is still okay. Remember, we only used 5 of 28 features and only 787 training cases. And we got 100% hit rate on non-fraud cases and 72% hit rate on fraud cases. And the test set was 197 cases in our case. Okay, let's maybe one step back. In general, there's a debate on whether QML makes sense or not. It's it's ongoing, I would say. Through entanglement and superposition, you get a transformation of the data to a high-dimensional Hilbert space, which allows possible easier separation of the data and therefore classifications. This works on NISC devices, which is great. Yeah, so we use this in the near term now today. But it's still under academic analysis. It seems that the separation can be easier, but as classical machine learning scales so easily, it can often outscale quantum algorithms. So if a quantum algorithm of the same size is better than a machine learning algorithm, and there are papers going into this direction and also evidence, the problem, or let's say if you just double the size of the classical network, a neural network, for instance, to do this analysis, then you can make up for you can just take over, you can outscale the quantum algorithm. So with that, we also concluded the VQC QML algorithm. Now, as a final part here, let's have a quick look at what's going on at the moment. What are our peers doing in banking? What time horizon are we talking here, and how could we start with this new technology? This is an overview of publications on POCs within the finance space. It's grouped by algorithm and domain. Where possible, the data is the publication date of the published article or paper. And there are quite some banks already experimenting with quantum, as you see, and the number is rapidly growing. Here we have an overview. Practically, quantum in finance is a stage journey. Build now, exploit selectively as hardware improves, and harvest real impact in the long term. To be short on this one here. So don't underestimate the learning time. You need to have some time. You need to understand how this model works and how to make use of it. And you also need to have a good overview of what's going on in research. There is every second month there is a new improvement coming out for QAOA or for other algorithms which can be tested and applied to own data and own cases. So it's super exciting at the moment. This takes time, and you need to understand what you're doing. Yeah, and then you can start exploiting and even harvesting them in the longer term, not too far. If you ask what the right focus is for 2026, I'd say the answer is not deployment, but capability building. The priority is education, structured experimentation and learning, where quantum methods help and where they clearly do not. That means simulator-first workflows, careful hybrid experiments, and clear decision criteria for stopping or scaling proof of concepts. Done right, this turns isolated demos into lasting institutional knowledge, and that's what you're looking for. Yeah, it's not just an isolated proof of concept delivered by an external company, but you need to build the knowledge within the corporation, and then you can build on that. In short, 2026 is about enabling informed judgment, not shipping quantum solutions. Thank you for your attention. I'm happy to take questions or dive deeper into any part of the discussion. Thank you and have a nice day.